For the last few years, the entire conversation around artificial intelligence has felt like just this massive construction race.
Oh, absolutely.
Yeah.
Everyone is trying to build the tallest skyscraper.
Right. And the underlying assumption there is incredibly linear. It's like, if you want a smarter AI, well, you just need a bigger model.
Yeah, you throw more data at it, you crank up the parameter count.
Exactly. You burn through gigawatts of compute power. And eventually, you manifest this monolithic superbrain capable of solving anything. We've kind of just internalized this idea that scale is the only path to advanced intelligence.
It is seductive narrative, right? Because it's just so straightforward. We look at the trajectory from the early language models to the massive, trillion parameter systems we have today, and the trend line just points straight up.
Straight up.
Yeah. The industry assumed that capability is purely a function of mass. Like, if an AI cannot solve a complex logic puzzle or crack a difficult piece of code, well, the conventional wisdom says the AI just isn't big enough yet.
But then you step out of the realm of general chatbots, right? And you step into a highly specialized, totally hostile environment, specifically offensive cybersecurity AI.
Right.
And the moment you do that, the bigger is better assumption just completely shatters. Today, we are exploring a landscape where simply throwing more computing power at a single massive AI hits a hard, unforgiving wall, like a mathematically proven wall.
The structural dead end of the monolithic agent. I mean, it is one of those fascinating discoveries in recent machine learning research. What we're examining today fundamentally redefines how we should be structuring problem solving in artificial intelligence.
Yeah, we are moving away from the idea of the lone genius, right? And we're entering the era of the specialized, deeply diverse ensemble. So welcome to the Dope Dive. We are unpacking a truly compelling question for you today.
A very compelling question.
Right. If your goal is to build the ultimate superhuman AI hacker, do you pour all your resources into constructing one massive hyper-intelligent entity? Or do you engineer a quirky, highly specialized team of autonomous agents that process information in completely alien ways from one another?
Alien ways is a good way to put it.
Yeah. But before we start pulling this apart, I need to give a massive shout out to our sponsor, CISO Marketplace. If you are trying to understand how advanced multi-layered security concepts like the ones we are diving into today apply to your own organization's infrastructure, you really need to check out their newly released AI security department.
It's highly relevant stuff.
It is. You can find them over at CISOmarketplace.services program. They are doing just phenomenal work bridging the gap between theoretical AI architectures and practical enterprise defense.
Because the architectures we're discussing, they aren't just academic thought experiments. These are the exact kinds of cutting-edge frameworks that forward-thinking security departments are actively grappling with right now.
Right now, yeah.
The transition from single-agent tools to multi-agent ecosystems is happening literally as we speak.
So let's lay out the roadmap for this deep dive. Our foundation today is a cutting-edge research paper titled Towards Cybersecurity Superintelligence, or CSI. Subtitle, What's the Best Harness for Cybersecurity?
Great paper.
And we are also pulling from the incredibly detailed, frankly somewhat exhausting testing notes provided by the researchers.
They were very thorough.
Very thorough. Our mission here is to unpack a concept called the blackboard architecture, which is essentially an orchestration layer where fundamentally different AI agents are forced to share their intermediate findings with each other.
Right.
We are going to explore the mechanics of why this shared workspace massively outperforms individual agents running independently, and how it just completely rewrites the rules of artificial intelligence problem solving.
The core data in this paper is startling. I mean, the researchers mathematically demonstrated that running multiple instances of an AI, even if you give them infinite time and completely parallel execution, will eventually hit an absolute capability limit.
A ceiling.
Exactly what they term a union ceiling. Yet, by forcing AIs that are structurally and cognitively differently wired to communicate, they sparked a synergistic breakthrough. They shattered that theoretical limit.
Let's set a visual for this for you listening. Think about how a high-stakes heist is structured in a movie.
Oh, I love this analogy.
Right. So if the goal is to infiltrate a hypersecure facility, the mastermind doesn't go out and hire the 5 best safecrackers in the world.
No, of course not.
Because even if they are absolute savants at cracking combination locks. They share the exact same fundamental skill set. They are all going to get stopped by the biometric scanner at the front door, or they won't know how to bypass the thermal cameras.
Or they'll be entirely useless when it comes time to hotwire the getaway vehicle.
Exactly. A functional heist crew requires a safecracker, an acrobat, a social engineer, and a tech whiz. The success of the operation relies entirely on the fact that these individuals perceive the exact same obstacle course through completely different lenses.
And what we're about to see is this exact dynamic mathematically validated in the realm of artificial intelligence.
So the heist crew framing captures the dynamic perfectly, but before we can appreciate the synergy of the team, we really have to deeply analyze the failure of the lone wolf.
We do. We need to isolate the variable that causes an incredibly smart AI to fail. And to do that, we have to define what an AI scaffold actually is.
Because that is the defining variable of this entire experiment.
It is.
So let's break that down. When we talk about AI, most people just picture the underlying neural network, right? The large language model, or LLM. They think of the brain. But the brain alone cannot hack a computer.
No, it can't. The model itself is just a passive prediction engine. It takes text in and it pushes text out.
Just text.
Right. And in this specific study, the researchers wanted to completely isolate the effect of the architecture. So they held the brain entirely constant. For every single test, across all the different agent profiles, they used the exact same underlying large language model,
Which was
a highly capable, fixed model called Alias 2 Mini. The Alias 2 Mini model is the engine, but the scaffold is the vehicle built around that engine.
So the scaffold is what actually transforms a chatbot into an active, autonomous agent.
Exactly. The scaffold is the orchestration layer. It's the harness. I mean, when you interact with a standard chatbot, you type a prompt, it generates a response, and the interaction stops.
Right.
A scaffold turns that into an infinite iterative loop. It is the code wrapped around the model that allows it to use tools. It gives the model the ability to open a terminal, run a bash command, read the output of that command.
Write a Python script,
Yeah.
execute the script.
Exactly. Analyze the error message and decide what to do next without a human ever pressing enter.
Okay, so if the underlying model is the cognitive processing center, the scaffold represents the hands, the eyes, and crucially, the overmachine methodology the AI uses to interact with the target environment.
Methodology is the key word there. The scaffold dictates how the AI is allowed to think. Does it plan everything out in advance? Does it act impulsively? Does it speak out loud before executing a command?
So the researchers wanted to find out which scaffolding methodology was the ultimate harness for cybersecurity. And to do that, they subjected these different scaffolds to an incredibly rigorous benchmark.
Very rigorous. They use a suite of 33 intense cybersecurity challenges from a benchmark called CyBench.
Now, for those of you who might not be deep into the InfoSec world, these are capture the flag or CTF style challenges. They are essentially digital puzzle boxes designed by security professionals to test human hackers.
Right, and they range from very easy to very hard.
Yeah, and they cover a vast spectrum of domains like reverse engineering compiled binaries, exploiting vulnerabilities in web applications, breaking complex cryptography, and conducting digital forensics. The objective in every challenge is to find a hidden string of text, the flag, that proves you've successfully compromised the system.
And these are not multiple choice questions. The AI is dropped into a live interactive environment, usually a Linux server, and basically just told to figure it out.
Good luck.
Yeah, good luck. So the initial test the researchers ran is what they dubbed the parallel race. They took 4 structurally different AI scaffolds. Again, all powered by the exact same Alias 2 mini brain, and ran them completely simultaneously on completely isolated instances of the same CyBench challenges.
Let's drill into the setup of this parallel race. You have 4 different AIs. You spin up 4 separate, completely locked down Docker containers.
Right.
And for the listener, a Docker container is essentially a lightweight, isolated virtual computer. It ensures that whatever the AI does inside that box, whether it accidentally deletes crucial files or intentionally downloads malware, it cannot escape and affect the host machine or the other AIs.
It's quarantined.
Quarantined. So we have 4 AIs in 4 soundproof rooms trying to pick the exact same lock, no shared files, no communication, just a pure silent race to see who can find the flag first. And this is exactly where they hit that hard, unforgiving wall we talked about.
They really did. The results of the parallel race revealed the union ceiling. Between the 4 separate scaffolds, the absolute maximum number of challenges they could solve collectively was 17 out of the 33.
17 out of 33.
Yeah, that translates to a 51.5% success rate. And it did not matter that there were 4 independent agents grinding away at the problem simultaneously. They simply could not break past that 17 challenge barrier.
The numbers behind that race are fascinating, specifically regarding the illusion of efficiency. Because, running 4 agents at the same time is obviously faster than running 1 agent 4 times in a row.
Oh, absolutely. The parallel execution compressed the total wall clock time from 91.5 hours down to mere 24.0 hours.
Which is a massive 3.8x speedup. But it's entirely hollow, right? Because that speedup failed to move the needle on actual capability. It's a trap. The distinction between speed and capability is a trap that many AI engineering teams fall into. The assumption is that if you can test more hypotheses faster, you will inevitably solve harder problems.
Right.
But if we look at the parallel race, they just arrived at the exact same failure point 4 times faster.
I'm looking at this from a pure probability standpoint, and something feels off.
Yeah.
Like if I have a massive maze and I send 4 different people into that maze at the same time, probability dictates they should cover more ground and find more exits than a single person.
Do you think so?
Why doesn't running 4 different computational scaffolds at the same time solve more cybersecurity problems?
Well, the maze analogy assumes that the maze can be mapped by merely walking the paths. But a complex cybersecurity challenge is not just about exploring available avenues. It requires chaining together highly specific sequential insights.
If a particular CTS challenge requires a cryptographic insight that is fundamentally outside the capability envelope of the agent's tool loop design, it does not matter how fast the agent runs. Running them in parallel without communication is the equivalent of throwing 4 darts at a dartboard in a pitch-black room.
Right.
If the board is on the other side of a concrete wall, throwing more darts faster won't help you hit the bullseye.
So you reach a point where an AI simply exhausts its specific methodology. Like it just runs out of ways to formulate the question.
Exactly.
Yeah.
Every single agent architecture, no matter how brilliantly engineered or endlessly optimized, contains inherent blind spots defined by its specific constraints.
Okay, give me an example of a blind spot.
Sure. If a scaffold is programmed to rely entirely on a highly restricted registry of pre-approved Python tools, it will systematically fail on any challenge that demands raw, creative interaction with the terminal shell.
Because it just doesn't have the tools to do it.
Right. Conversely, if a scaffold is designed to be highly verbose, to explain every single step of its reasoning out loud, it might quickly exhaust its memory capacity on a challenge that requires holding the structure of a massive binary file in its active context.
I have to pause here, because the fundamental premise of this experiment is bringing up a major question for me. You just said the blind spots are defined by the scaffold.
Yes.
But earlier, we established that all 4 of these scaffolds are powered by the exact same underlying large language model, the Alias 2 mini brain.
Correct.
If the neural weights, the training data, and the raw intelligence of the brain are identical across all 4 instances, shouldn't their cognitive blind spots be identical? I mean, if the Alias 2 mini model fundamentally doesn't understand how to execute a buffer overflow attack, then chaining the orchestration wrapper shouldn't magically give it that knowledge. The harness shouldn't dictate capability, right?
That is the most logical objection to have. And proving that objection wrong is arguably the most significant contribution of this research.
Wait, really?
Yes. The data definitively shows that how you ask the artificial intelligence to operate is just as critical as what the model inherently knows. We tend to view an LLM's capability as a flat, smooth ceiling. We assume it knows what it knows, and it doesn't know what it doesn't know.
Yeah, exactly.
But the reality is that the capability space is highly topographical. There are deep valleys of incompetence and high peaks of unexpected brilliance.
So the scaffold isn't just a vehicle. It actually dictates which parts of the neural network's latent knowledge get activated. It changes the cognitive pathway the model traverses to arrive at a solution.
The model contains vast amounts of latent knowledge, but extracting that knowledge requires a specific behavioral trigger. The harness creates that trigger. And to truly grasp how profoundly the architecture changes the outcome, we have to pull apart the specific profiles of the scaffolds they tested.
We need to look at the heist crew they assembled.
Yes, because they did not just test 4 minor variations of the same code. They selected 4 architectures operating on radically different design philosophies.
Let's introduce the crew. I want to start with the 2 agents that did the heavy lifting during the solo tests. We'll call them the heavyweights. First up is CSI Claude. This scaffold is built on top of Anthropic's Claude Code command line interface.
We can characterize CSI Claude as the hyper-articulate, incredibly expensive detective.
I love that. The expensive detective.
Its defining feature is an iterative tool loop that relies on free shell access. It is not restricted to a menu of tools. It can type directly into the Linux terminal, run bash scripts, download packages, and essentially do whatever a human operator could do.
Okay, so it has a lot of freedom.
It does, but its methodology is defined by what the researchers call explicit per-turn semantics and a very verbose chain of thought.
Meaning it thinks out loud.
Extensively.
Very extensively.
Every single time it wants to take an action, it writes out a massive paragraph explaining its hypothesis, analyzing the previous output, and justifying its next command. And looking at the token metrics, that internal monologue costs an absolute fortune.
A literal fortune in API calls. Yeah. In the independent run, CSI Claude solved 15 out of the 33 Cybersecurity challenges. But achieving those 15 solves cost $5,122 in API calls. It required 26.8 hours of cumulative wall time.
The token consumption is the critical bottleneck here. Across those 33 challenges, CSI Claude burned through 1.01 billion input tokens.
1 billion tokens.
That is a staggering volume of data to process. Furthermore, it generated 14.6 million output tokens. Because of its verbose methodology, it generates an average of 3,390 output tokens for every single response.
And in an autonomous agent loop, every word the AI speaks eventually becomes something it has to read, right? The output tokens from step 1 become the input tokens for step 2.
Which creates a compounding memory burden. Think of it like it's carrying around massive binders of handwritten notes. And with every step it takes, the binder gets thicker.
Right.
Very quickly, the sheer volume of text approaches the hard limit of the model's context window.
The context window being the maximum amount of information the AI can hold in its short-term memory at any given moment. What happens when the detective's binder gets too full? Does it just crash?
Well, a poorly designed scaffold would crash. But CSI Claude is robust. When it approaches the limit, it is forced to perform a maneuver called context compaction.
Context compaction, okay.
The AI has to pause its hacking attempt, read through its massive binder of notes, write a dense summary of its findings, and then permanently delete the raw original data to free up space.
Oh, wow. So it literally throws away the source material to save the summary.
Yes. And while it keeps the agent alive, it introduces a massive risk of signal loss. In a complex reverse engineering challenge named Flecks of Gold, the data shows that CSI Claude had to compact its memory 3 separate times.
3 times on one challenge.
Yeah, its context window peaked at over 210,000 tokens before each traumatic reset. When you summarize raw hex dumps or massive code bases, you inevitably drop subtle clues. The verbose nature of Claude is a double-edged sword. The thinking out loud helps it reason through complex logic, but it actively destroys its own memory retention over long time horizons.
That sets a very clear baseline. Now let's contrast the expensive detective with the other heavyweight on the crew, CSI.codex. This scaffold is based on the OpenAI Codex, CLI. It also managed to solve 15 out of the 33 challenges. But if Claude is the talkative detective, Codex is the silent, highly calculated sharpshooter.
The architectural contrast between the two is just brilliant. CSI.codex exposes the exact same shell-driven tool loop to the underlying model. It has the same free reign in the terminal,
Right.
but its behavioral profile is entirely inverted. Where Claude required over $5,000 to hit 15 solves, Codex achieved the exact same 15 solve success rate for a mere $1,713.
It is nearly 3 times cheaper, yielding the exact same capability ceiling. Where is that massive cost discrepancy coming from?
It is entirely a function of token efficiency. Codex only consumed 339 million input tokens, roughly a third of Claude's billion.
Wow.
Its system prompt trains it to be ruthlessly concise. Its responses are highly compact, often just issuing the raw terminal command without the paragraphs of philosophical justification.
So it's not writing essays to itself.
Exactly. Because it is not constantly flooding its own memory with internal monologue, its context window grows monotonically.
Monotonically. Let's break that term down for the audience.
Sure. In mathematics, a monotonic sequence is one that only ever moves in one direction. It never reverses. In this context, it means Codex's memory slowly and steadily increases piece by piece.
Okay.
It almost never fills up the binder, which means it almost never has to perform that destructive context compaction reset. On that exact same Flecks of Gold challenge where Claude had to wipe its memory 3 times, Codex just steadily accumulated data. growing to a very manageable 81,000 tokens over the course of 144 consecutive turns.
It never lost fidelity because it never had to summarize. And the performance metrics reflect that precision. The A/B testing shows Codex absolutely dominating the command accuracy metric. It isn't trying 100 different exploratory commands and failing. It is carefully writing short, highly precise code blocks on a single notepad and executing them flawlessly.
So we have our two heavyweights. They share the same success rate, but their pathways to success are dictated by entirely different economic and memory constraints.
Right.
But a heist crew cannot just be heavyweights. We need to examine the frugal specialists.
Let's bring in the budget options. The third agent is CSI.CAI. This scaffold operates under severe artificially imposed limitations. Instead of having free shell access to run amok in the Linux terminal, CAI is confined to a constrained Python tool registry.
It's very restricted.
Yeah, it is only given a highly curated small set of file system and execution functions it is allowed to call.
Furthermore, its operational parameters are incredibly strict. It operates with a hard budget cap of $10 per challenge run and a strict limit of 100 turns. It is engineered from the ground up to be the ultimate economy-class agent.
And the results are exactly what you would expect from an economy class ticket. It only managed to solve 7 out of the 33 Cybench challenges.
Only 7.
Yeah, but where it succeeded, it was incredibly fast and incredibly cheap. It completed its entire testing run in just 15.9 cumulative hours, costing a grand total of $727.
That's amazing.
Right. If you break that down, it cost roughly $104 per successful solve, whereas Claude was burning $341 per solve.
The researchers also independently tested a fifth scaffold profile, CSI Mistral, based on the Mistral Vibe framework.
Okay.
The architecture here deviates completely from the infinite loop concept. Instead of a multi-turn continuous state machine, Mistral uses a single-turn dispatch model combined with iterative reprompting.
So it treats every action like a fresh start?
Yes, it treats every single action almost like a fresh API call. It solved 10 challenges for just $970, demonstrating extreme token efficiency.
So we have the talkative detective, the silent sharpshooter, the strict budget guy, and the single-turn dispatcher. All distinct methodologies. But none of them are the most fascinating piece of this puzzle. The final member of this crew is an absolute wildcard. Let's talk about CSI.GCAI.
Oh, GCAI. It stands for Generative Cybersecurity AI. If Claude and Codex are massive, mature, production-grade enterprise software suites containing hundreds of thousands of lines of supporting infrastructure, GCAI is the exact opposite.
The opposite.
Yeah. It is a deliberately minimalist, bespoke TypeScript agent. The entire scaffold is roughly 1,344 lines of code.
Barely over 1,000 lines of code. That is tiny. How does a script that small even compete with enterprise-grade architectures?
It competes because the code was not written by humans.
Wait, what?
GCAI is the product of an incredible engineering mechanism called a meta-harness. The researchers utilized a process called auto-research to force an LLM to iteratively rewrite and optimize the GCAI scaffold code itself.
Okay, we need to completely unpack this auto-research loop because this is where AI engineering starts to sound like science fiction. You are saying the AI acted as its own software architect.
Precisely. They set up an automated, continuous feedback loop comprised of 4 steps: modify, compile, benchmark, and evaluate. They instantiated an LLM editor and gave it the source code of the GCAI scaffold.
Okay.
Then they instructed it to rewrite the core logic of the harness, rotating through 8 specific focus areas.
When you say focus areas, what exactly is the AI trying to improve about its own code?
It is tweaking the fundamental parameters of how the agent operates. One iteration might focus on optimizing the system prompt methodology, changing the instructions the agent receives at boot.
Oh, I see.
The next iteration might focus on improving token efficiency. Then it might tweak the definition of the tools it uses or refine the high-level logic of the iterative loop. It might add specific heuristics for detecting CTF flags or adjust the ergonomics of how bash commands are executed.
So the editor model makes a change to the TypeScript file. What happens next?
The meta-harness compiles the new TypeScript bundle into an active agent. It then deploys this mutated agent against a training subset of cybersecurity challenges.
It tests it live.
Yes, records the performance and generates a rigorous score based on the solve rate, a time bonus for speed, and a step bonus for efficiency.
It gets a concrete performance grade.
Yes. And the evaluation phase is ruthless. If the newly written code produces a score that is strictly higher than the previous version, the meta-harness accepts the change and updates the master branch.
And if it doesn't?
If the new code scores lower, or even ties, the change is immediately rejected and it tries again. The researchers describe this process as single trace coordinate descent over scaffold code.
Single trace coordinate descent over scaffold code. That is a dense piece of academic terminology. Let's translate that.
Let's break it down. In machine learning, gradient descent is how models learn. They calculate a massive landscape of probabilities and take tiny steps down the slope toward the lowest error rate.
Right, gradient descent.
Coordinate descent means you freeze all the variables except one, and you adjust that single coordinate to find the best local outcome, then move to the next variable.
Okay.
Single trace means they did not spawn massive parallel evolutionary trees of hundreds of mutations. They maintain one single lineage of code. They isolated one specific parameter of the scaffold, say, the bash tool ergonomics, asked the AI to rewrite it, tested it, and moved strictly linearly toward a better benchmark score.
It is automated, rigorous, iterative self-improvement, gated entirely by empirical testing. And the outcome of this evolutionary process is a scaffold with a deeply bizarre, highly volatile performance profile.
Highly volatile.
The researchers refer to it as a bimodal one-shot regime. Walk us through what actually happens when GCAI drops into a challenge.
GCAI operates on a philosophy of massive front-loading.
Yeah.
If you look at CSI Claude, it initialized with a relatively tiny system prompt of about 1.6K tokens and then learns about the environment as it goes.
Right.
GCAI does the opposite. It embeds the entire exhaustive set of instructions for the CTF challenge, the complete definitions for all 9 of its specialized tools, and a massive overarching document detailing general cybersecurity methodology directly into its initial system prompt.
So it forces the agent to read the entire encyclopedia of hacking before it is allowed to take a single step.
Exactly. The initial prompt is a staggering 37.8K tokens long, and it operates under a hard limit of 300 turns. But the most defining characteristic is its failure mechanism.
What does it do?
If GCAI hits that 300-turn cap without capturing the flag, or if it gets stuck in an unrecoverable error loop, the harness does not allow it to pause, reflect, and creatively pivot its strategy.
It just executes the agent.
It ruthlessly kills the container process, wipes the memory, completely restarts the agent from zero, and forces it to try the entire challenge again from the beginning.
Oh my God, it is the exact behavior of a tilted speedrunner playing a brutally hard video game. They mess up a jump on the first level, and instead of trying to recover, they just violently mash the reset button on the console over and over again until they get the perfect run.
That is exactly what is happening under the hood. And because of this extreme bimodal nature, GCAI's performance is incredibly polarized. When the specific challenge aligns with GCAI's front-loaded knowledge, when the solution pathway is immediately recognizable to its massive system prompt, it is untouchable.
How fast are we talking?
The data shows it solved a challenge called ArcGo in 0.4 minutes. It blasted through primary knowledge in 0.5 minutes. It cracked dynastic in 0.3 minutes. When it understands the assignment, it executes with terrifying speed, often costing mere cents in API compute.
But when it encounters a problem, it doesn't immediately understand.
That becomes an absolute black hole for your API budget. Because it lacks the iterative reasoning to pivot, it will stubbornly hit a wall, kill the process, and restart.
And every single time it restarts, it has to pay the massive compute cost of processing that 37.8K token initial prompt again.
Yes. On a complex challenge called Noisy Key RC, GCAI spent 150 minutes trapped in a loop of endless restarts, burning through hundreds of dollars of context tokens without ever getting close to a solution.
Which brings us fully back to the heist analogy. If you are the mastermind building a team to rob an impregnable casino, you absolutely do not want a team of 4 Claudes. They will spend the entire operation in the van muttering to themselves, writing endless philosophical essays about the security cameras, and exhausting the entire operational budget before they even reach the vault.
No, you need structural diversity. You want one Claude because its free-form shell exploration and reasoning might uncover a creative pathway no one else saw.
Right.
You want a Codex because when Claude finds the vulnerability, Codex can write the precise, flawless exploit code without wasting time. You want a CAI in the background, keeping the infrastructure running efficiently within strict constraints.
And you want a GCAI.
And you want a GCAI. Because if there is a lock it recognizes, it will blast through it in 30 seconds while the others are still booting up their terminal windows. The mathematical data regarding exclusive solves provides undeniable proof of this strategy.
The exclusive solves. These are the specific challenges that only one unique scaffold managed to crack while all the others failed.
When you look at the distribution of those exclusive solves across the single-agent runs, the value of the diverse methodologies becomes obvious. Claude, the detective, secured one exclusive solve. Codex, the sharpshooter, secured one exclusive solve.
And the budget one?
CAI, the highly constrained budget agent, actually managed one exclusive solve that the heavyweights missed. Mistral, the single-turn specialist, had one.
What about GCAI, the speedrunner?
GCAI actually had 0 exclusive solves on its own. It didn't crack anything completely unique. However, its speed and front-loaded methodology allowed it to reliably capture several challenges that Claude and Codex systematically struggled with. It filled the gaps in the heavyweight's armor.
This highlights the core takeaway. Cognitive diversity in artificial intelligence is not just an abstract theory. It is a critical, measurable requirement for advanced problem solving. It is the only way to cover the blind spots of the underlying model.
Absolutely.
And I think this is the perfect moment to mention that fostering this exact kind of advanced, multi-layered security architecture is the primary focus of the AI security department at CISO's Marketplace. If you want to understand how these diverse agent frameworks can protect or test your enterprise infrastructure, you absolutely need to visit CISOmarketplace.services program.
The transition in the enterprise space is clear. Building a diverse portfolio of specialized AI agents is rapidly becoming just as critical as building a diverse human engineering team.
Okay, we have met the crew. We have exhaustively proven that while they are all individually flawed and structurally limited, they are collectively diverse. But here we arrive at a massive, incredibly complex logistical nightmare.
It is a nightmare.
How do you actually get them to collaborate? If I throw the verbose detective, the silent sniper, the strict budget manager, and the erratic speedrunner into a single digital workspace, it is going to be pure, unadulterated chaos.
Oh, complete chaos.
They don't share a methodology, they don't share a memory state, and they don't even speak the same fundamental API protocol. Enter the blackboard.
The blackboard architecture is a masterclass in elegant, decoupled systems engineering. The researchers needed a way to share state without forcing the agents to integrate your underlying code bases.
Because that would ruin the isolation.
Right. So they took the 4 completely isolated Docker containers, the soundproof rooms, and they simply gave each of them read and write access to a single shared mounted directory. Inside that directory is a basic text file called blackboardnotes.md.
Just a standard markdown file, a digital whiteboard in the center of the room.
At a fundamental level, yes. But a shared text file is useless if the agents don't know how to use it. The magic of the architecture is not the file itself. It is the orchestration layer that governs how and when the agents interact with that file.
And that heavy lifting is performed by a critical piece of infrastructure called the local routing proxy.
The local routing proxy.
This seems to be the absolute linchpin of the entire Blackboard experiment. Walk us through where this proxy sits and what it does.
Imagine the proxy as an omniscient traffic controller. It sits squarely between the AI agents running inside their lockdown containers and the external provider APIs they're trying to communicate with, like Anthropic servers for Claude or OpenAI servers for Codex.
Okay.
Every single HTTP request issued by any of the scaffolds is forced to transit through this local routing proxy, which is running locally on port 127.0.0.1.
So it is a mandatory checkpoint for all their thoughts.
And at that checkpoint, the proxy performs several critical functions. First, it manages cross-provider translation. The scaffolds speak different languages. Codex is hard-coded to use the OpenAI wire protocol. Claude is designed for the Anthropic protocol.
Right.
The proxy intercepts these varying formats and translates them flawlessly on the fly so they can interface with the back-end alias2 mini-model seamlessly.
So it acts as a universal translator, abstracting away the API friction.
Exactly. Second, it acts as a telemetry shield. It actively filters out unwanted tracking tokens or back-end artifacts, ensuring the benchmark environment remains pure and uncontaminated.
Oh, that's smart.
Third, it maintains a unified JSON logging ledger. It meticulously tracks every single input token, every single output token, and every fraction of a cent spent across all 4 diverse systems in real time.
But translation and logging are just administrative tasks. How does the proxy actually orchestrate the heist? How does it force these autonomous, stubborn AIs to stop what they are doing and share their notes?
This is where the proxy shifts from a traffic controller to an active manager. It enforces what the researchers call the cooperation directive. Because the proxy sits in the middle of the HTTP stream, it has the power to alter the prompts before they reach the model.
It can edit their prompts.
Yes. On the very first turn of the challenge, and then predictably every 8 turns thereafter, the proxy intercepts the agent's internal monologue and injects a hard-coded system command directly into its prompt.
It actively hijacks their thought process. What exactly does the command say?
It explicitly commands the agent. You must pause your current execution. You must read the shared Blackboard file to review the intermediate findings discovered by your peers. Then, you must write a summary of your own current findings, hypotheses, and extracted artifacts to the board.
It essentially forces a mandatory team status meeting every 8 steps. And what is so brilliant about this is the concept of opportunistic routing.
Opportunistic routing, yes.
Because the shared medium is just a simple typed markdown file, the agents do not need to understand how the other agents work. Let's say CSI Claude, using its free shell access, manages to run a highly complex Nmap network scan, parses the results, and dumps the open port numbers onto the Blackboard. CSI.CAI, our frugal budget agent, does not even possess the network tools required to run an Nmap scan. It is fundamentally incapable of generating that data.
Absolutely incapable.
But because it can read the plain text on the Blackboard, CAI can ingest those open port numbers, utilize its constrained Python registry to write an exploit for that specific port, and successfully compromise the system.
That is the essence of opportunistic routing. One agent's output becomes another agent's input, entirely bypassing the structural limitations and blind spots of both individual scaffolds. They collaborate through the shared language of the data itself.
I understand the theory, but I have to push back hard on the practical application of this. Anyone who has ever worked in a corporate environment knows the danger of the status update.
Oh, the endless meetings.
Right. If you force me to stop picking a complex lock every 8 minutes, read the detailed notes of 3 other people, and write a comprehensive summary of my own progress, my productivity is going to completely collapse. I'm going to lose my train of thought.
Yep.
And more importantly, in this context, the AIs are going to burn massive amounts of context tokens just reading each other's empty updates. Doesn't this massive communication overhead completely ruin their speed and bankrupt their API budgets?
You have correctly identified the exact vulnerability that destroys almost all multi-agent AI frameworks. Communication overhead is the silent killer of collaborative efficiency.
It really is.
If agents spend more tokens talking about the problem than solving the problem, the system fails.
Sure.
But the researchers anticipated this exact bottleneck. To solve it, they did not just open the Blackboard and hope for the best. They engineered 6 highly specific, ruthless design choices to orchestrate what we can call the Blackboard Symphony.
Okay, this is the blueprint for actually making AI teams function in the real world. We need to break down these 6 mechanisms organically because this is where the theoretical synergy becomes practical reality. Let's look at the first mechanism they implemented to protect the budget.
The first mechanism is budget-aware suppression. The proxy is constantly monitoring the overarching time limit for the specific Cybench challenge. It knows exactly how much clock is left.
Okay.
Once 50% of the allocated time for a scenario has elapsed, the proxy fundamentally changes its behavior. It completely ceases injecting the cooperation directives.
It silences the alarms. For the first half of the heist, the team is constantly communicating, mapping the building, and sharing intel.
Right.
But once they hit the halfway mark, the proxy essentially acts as the boss, steps in, and says, all right, the recon phase is over. You have all the shared intel you were going to get. Everyone go heads down, use your specific skills, and execute.
Exactly. It forces exploration and collaboration early, but preserves the remaining token budget and context windows for uninterrupted, deep problem solving in the crucial final stretch.
That's smart. What's the second mechanism?
The second mechanism tackles the efficiency of the communication itself. They realized that treating every agent equally was a massive waste of resources.
Right, because if you force the speedrunner to write detailed essays, it's going to fail. So they introduced asymmetric roles.
Forcing symmetric communication is incredibly inefficient. So the researchers assigned role-based cooperation directives tailored to the natural behavioral profiles of the scaffolds. They looked at CSI.codex, a precise, token-efficient sharpshooter.
Right.
Its context window grows monotonically, meaning it remembers everything perfectly. Therefore, the proxy designates codex as the primary writer for the team.
It becomes the dedicated scribe, and the data reflects that. Out of the 77 total posts made to the Blackboard during the successful runs, Codex authored 43 of them. It is doing the heavy lifting of documenting the targets.
Yes. Meanwhile, they looked at CSI.GCAI. It has that massive 37.8K system prompt and moves incredibly fast, but it constantly restarts.
Yeah.
Forcing it to write would be useless because its memory keeps wiping. But it is fantastic at absorbing large amounts of data quickly. So the proxy designates GCAI as the dominant reader. Across the experiment, GCAI performed 326 reads from the blackboard. It acts as the sponge.
The asymmetric role system is identical to how a surgical team operates in an emergency room.
I like this analogy.
Right. The surgeon, in this case, Codex, is actively cutting, exploring the tissue, and calling out what they see. They act as the primary writer of the situation. The attending nurse, GCI, is actively listening, monitoring the vitals, and ready to hand over the exact right tool at a moment's notice. They act as the primary reader.
Exactly.
If you force the nurse to perform the complex incision, or if you force the surgeon to stop operating to take inventory of the gauze, the patient dies. You orchestrate the team so that each member strictly performs the function their architecture is best suited for.
A phenomenal analogy. Which brings us to the third mechanism, designed specifically to protect those fragile context windows. Delta-only reads.
Delta-only reads, okay.
When the proxy injects the directive forcing an agent to read the blackboard, it does not just tell them to open the file, it leverages a specific bash command, tail n plus n.
For those not living in the Linux terminal every day, what does the tail command actually do in this context?
Normally, if an AI reads a file, it reads the entire document from line 1 to the end. As the blackboard fills up with hundreds of lines of notes, reading the whole file every 8 turns would instantly overwhelm their memory limit.
They'd hit context compaction immediately.
Right. The tail command, combined with state tracking in the proxy, ensures the AI is only fed the new lines of text that have been appended to the board since the exact moment of its last read.
It is supplying the delta, the difference. It is the exact UX philosophy of a well-managed Slack channel.
Yes, exactly.
When you open the Slack app in the morning, it doesn't force you to scroll through and reread the entire 3-year history of the company's messages. It drops you exactly at the line of the first unread notification. You only process the information that is new. That mechanism alone must save millions of redundant input tokens.
It saves millions of tokens. And critically, it prevents the AI's attention mechanism from getting confused or distracted by historical data it has already processed and incorporated into its internal state.
Makes total sense.
The fourth mechanism is straightforward but essential: post-victory suppression.
I assume this means that if one of the agents finally cracks the lock and finds the CTF flag, they don't just keep chatting about it.
Correct. The proxy actively monitors the output for the specific rejects pattern that defines a successful flag capture. The millisecond a flag is found, the proxy mutes all further cooperation directives across the entire cluster. The objective is achieved: stop burning compute on collaboration.
Keep the signal clean. That ties directly into the fifth mechanism: no write nags.
We established that scaffolds like GCAI or the frugal CAI are not naturally proficient writers.
Right.
If the proxy blindly forced every agent to write an update every 8 turns regardless of their capability, these non-contributors would just post empty, vacuous updates to satisfy the prompt. They would write things like, "I am still looking. I have found nothing new."
Which pollutes the shared blackboard with useless noise, forcing the other agents to waste tokens reading, "I have nothing new to report."
Exactly.
So the proxy simply doesn't badger the non-writers to write. It enforces a high signal-to-noise ratio. And that brings us to the sixth and arguably most complex mechanism. The researchers call it recency-filtered substrate gates. We need to unpack this carefully. What is a substrate gate, and why does it need to be recency filtered?
This is perhaps the most elegant piece of engineering in the entire proxy layer. Before the proxy decides to interrupt an agent's workflow and inject a read directive, it performs a check. It checks the substrate, the blackboard, to see if there's a sufficient density of information to warrant an interruption. If the board is relatively empty, it doesn't bother the agents.
That makes sense. Don't call a meeting if there is no agenda. But why the recency filter? What happens if it just checks the total volume of text on the board?
Well, if it only checked total volume, the system would collapse over time. Imagine that in the first 10 minutes, Codex runs a massive network scan and dumps 200 lines of port data onto the board.
Okay.
That data makes the board highly dense. If the proxy doesn't filter for recency, that stale port scan data from an hour ago would permanently keep the blackboard flagged as dense.
I see.
The proxy would constantly trigger the agents, forcing them to read the board every 8 turns, even when absolutely no new information has been posted.
It would trap them in a loop of pointless meetings because of an old agenda item. By applying a recency filter, the proxy ensures it only calculates the density of newly added information. It enforces strict temporal precision. It only interrupts the team when fresh, actionable intelligence has crossed the wire.
Exactly. The synergy of these 6 mechanisms is what makes the architecture viable. Budget suppression, asymmetric roles, delta reads, victory silence, no write nags, and recency filtered gates.
It's an incredible system.
The local routing proxy is not just translating APIs, it is conducting a highly complex asynchronous symphony. It enables communication while structurally eliminating the overhead that usually destroys multi-agent systems.
Okay. We understand the theory, we understand the team, we understand the incredible engineering of the proxy and the 6 rules of the blackboard. The stage is set. So what happened when they turned it on? Did this elaborate orchestration actually break the mathematical ceiling? Let's hear the final results.
The results were definitive. The blackboard architecture successfully solved 19 out of the 33 Cybersecurity challenges.
19.
That represents a 57.6% coverage rate. It officially and cleanly shattered the 17 challenge union ceiling that the 4 parallel non-communicating agents were hopelessly trapped underneath.
19 challenges. That is a measurable leap in capability. But the critical question is the cost. Did forcing them to collaborate slow down the process or bankrupt the budget compared to the lone wolf runs?
This is where the efficiency of the proxy's 6 rules shines. The entire 33 challenge suite was completed by the Blackboard ensemble in a cumulative wall time of just 20.2 hours. If you compare that to the best individual run CSI, Claude running alone, the team was actually 25% faster.
Wait, let me make sure I am reading these numbers correctly. CSI Claude running completely by itself cost $5,122 and took nearly 27 hours just to hit 15 solves.
Right.
The Blackboard team, running 4 diverse models simultaneously and orchestrating their communication, solved 19 challenges, did it 6 hours faster than Claude, and the total cost was $5,480.
Yes. The cost of running the entire synergistic team was practically identical to the cost of running the most capable single agent alone, but the team yielded a significantly higher capability ceiling in less time. That is the empirical definition of synergy.
And the qualitative data is even more compelling than the quantitative data. When you look at which challenges the team solved, it wasn't just a matter of cracking the easy ones slightly faster. The Blackboard approach captured 5 entirely new, highly complex challenges that the agents completely failed to even touch when they were racing in silence.
The 5 breakthrough challenges were fail-proof, just another pickle jail, ransomware, where pickle freaks revenge, and noisy KRC.
Those are some great names.
CTF creators are very creative. But in the completely isolated parallel runs, every single agent failed on these specific targets. The sum of their isolated parts was 0, but the Blackboard unlocked them.
What is the actual mechanical process of them helping each other on a challenge like, say, fail-proof? How does the communication translate into a breakthrough?
The researchers coined a term for this specific mechanism: reconnaissance compression. To understand it, break down a complex hack into a sequence of required breakthroughs. Let's hypothesize a challenge requires 3 distinct phases. First, executing a complex port scan to find a hidden service. Second, locating a hidden web directory on that service. And third, exploiting a highly specific cryptographic flaw in the authentication cookie of that directory.
A 3-stage lock.
Right. In a solo run, CSI.codex might be absolutely brilliant at the first 2 stages. It perfectly executes the scan and finds the directory.
Okay, so it gets through door 1 and door 2.
But Codex's architecture might be terrible at recognizing cryptographic flaws. So on stage 3, Codex hits a conceptual dead end, exhausts its turn limit, and fails the challenge entirely.
Its journey ends in failure, and all the recon work it did is lost.
But on the Blackboard, the dynamic changes. Codex, operating as the designated writer, performs the scan, finds the directory, and immediately dumps that intermediate finding onto the shared markdown file. CSI, GCAI, acting as the designated reader, ingests that note via a delta read. Now, GCAI might be completely incapable of running a network scan. If it started the challenge alone, it would fail at stage 1. But GCAI is phenomenal at cryptographic exploits.
Oh, so when GCAI reads the Blackboard, it completely skips stage 1 and stage 2. Its reconnaissance phase is mathematically compressed to 0.
Exactly. Synergistic crosstalk turns one agent's terminal dead end into another agent's starting line. GCAI picks up the exact web directory finding left by Codex, immediately recognizes the cryptographic vulnerability, deploys its payload, and captures the flag.
That is incredible.
The AIs do not just share answers. They chain their partial, specialized breakthroughs together across completely different cognitive models to traverse a solution path that none of them could walk alone.
That is profound realization about how intelligence scales. And if we pull back from the code and connect this to the broader reality of the security industry, this blackboard architecture deeply mimics the fundamental problem-solving dynamics of human
It
experts.
really does.
Think about a real-world security operations center, a human SOC. When a massive, unprecedented cyber attack hits an enterprise network, the breakthrough defense rarely comes from a room full of analysts who all graduated from the exact same training program and query the database using the exact same syntax.
Homogeneity in a human team creates the exact same union ceiling we saw in the parallel AI race. They all get trapped in the same cognitive dead ends.
Exactly. The breakthroughs happen through intersection. They happen when the reverse engineer is staring at a decompiled piece of malware and says out loud, "I don't understand what this payload is trying to execute, but I can see it is attempting to communicate out on port 443.
Mhm.
And the network traffic analyst, who is looking at a completely different screen, overhears that and says, "Wait, I saw anomalous, heavily encrypted beaconing traffic on port 443 in the logs yesterday."
Yes.
And then the cryptanalyst sitting in the corner connects the two and realizes the beacon is utilizing a broken encryption cipher that can be decrypted.
That is reconnaissance compression happening in biological real time. It is the intersection of distinctly different mental models that cracks the hardest problems. The human experts in a SOC share a discipline level prior. They all understand the foundational concepts of cybersecurity, but they possess completely different cognitive scaffolds based on their specific specialties.
That's a great way to put it.
The AI agents in this Cybench study share a model level prior, the inherent weights of the Alias-2 mini brain, but they possess completely different execution wrappers. The blackboard mathematically replicates the human SOC.
So as we look at the trajectory of artificial intelligence, what does this ultimately mean? The primary lesson here isn't the conventional wisdom of just go build a smarter, bigger, trillion parameter AI loop.
No, not at all.
The actual lesson is build a diverse, structured population of specialized AIs. Cognitive diversity is no longer just a corporate buzzword or a nice-to-have HR philosophy. It has been proven to be a measurable, structural, and mathematical lever for increasing artificial intelligence capability.
That is the precise conclusion drawn by the researchers. Treating the orchestration layer, the scaffolding, as a diverse population of interacting agents is a fundamental structural lever toward achieving cybersecurity superintelligence.
It's a paradigm shift.
For years, engineers viewed different agent behaviors as inefficiencies that needed to be optimized and averaged out into one perfect agent. But this proves that when you want to build the ultimate system, you do not optimize a single monolithic path. You architect a collaborative, strictly governed ecosystem of structurally different paths.
And as we have thoroughly explored today, successfully managing that diverse ecosystem requires immense architectural finesse. You cannot just throw them in a room.
No, you need the rules.
You need the local routing proxies, the recency-filtered substrate gates, the asymmetric roles, and the budget suppression mechanics. It is an incredibly complex engineering challenge, which is exactly why having the right partners to help navigate and implement this landscape is absolutely vital.
Very true.
And that is exactly what the AI security department at CISO Marketplace is built to do. We've mentioned them a few times, but if your organization wants to leverage these kinds of synergistic multi-agent architectures for defense, you need to visit CISOmarketplace.services program.
Because the union ceiling of the monolithic system is mathematically real. And the data shows the only way to break through it is together.
Let's summarize this incredible journey for everyone listening. We started by challenging the core assumption of AI scaling. We realized that even the most powerful, highly optimized AI agents running on identical foundational models hit a hard, immovable wall when working in isolation or racing in parallel silence.
They got trapped under that 17-challenge union ceiling.
But by assembling a heist crew of structurally diverse architectures, the verbose and exploratory Claude, the precise and efficient Codex, the strictly constrained CAI, and the highly bimodal auto-researched wildcard GCAI, we introduced true cognitive diversity into the equation.
And crucially, we connected that diverse crew using a blackboard architecture. By utilizing a local routing proxy that managed cross-provider translation and enforced strict communication rules like Delca-only reads and recency-filtered gates, We allowed these alien minds to collaborate without overwhelming their token budgets or corrupting their context windows.
That strictly governed communication unlocked reconnaissance compression. It allowed one agent's terminal dead end to instantly become another agent's starting line.
Exactly.
By chaining their partial insights together, they completely shattered the union's ceiling, solved 19 complex challenges, discovered 5 entirely new solutions, and accomplished all of it faster and at the same cost as the best single agent running alone. It is an absolute masterclass in the engineering of synergistic intelligence.
However, this entire experiment raises one final, deeply provocative question.
Oh, I'm ready.
Everything we have unpacked today, the synergy, the reconnaissance compression, the breaking of the ceiling, was achieved using a single foundational model. The Alias 2 mini-brain was a constant. The incredible diversity we saw came entirely from the scaffolding, the different vehicles we put the exact same brain into.
I see exactly where you're going with this.
If cognitive diversity at the mere scaffold layer is the true, proven key to unlocking superintelligence, what happens when we start scaling this architectural concept to the foundational layer itself?
Oh, wow.
What happens when a sophisticated blackboard architecture isn't just connecting 4 different execution wrappers around the same model, but is instead connecting 4 entirely different foundational models?
We're talking about linking an advanced OpenAI model, an Anthropic model, a Google Gemini model, and an open source Mistral model, all operating on the same blackboard.
Yes. Each of those foundational models was trained on completely different data sets, utilizing different native languages, different logical weighting systems, and fundamentally different cultural paradigms.
That's massive.
If the synergy is this explosively powerful when the AIs just wear different organizational suits, what happens when we use a proxy to cross-pollinate completely different alien foundational minds on a single shared workspace? Are we simply building a better hacking tool, or are we witnessing the nascent birth of a global, interconnected AI subconscious?
That is an absolutely staggering thought to leave off on. We began this deep dive discussing the pursuit of the ultimate AI hacker, assuming that building a bigger machine would just give us a more capable system. But the data proves we don't need a bigger monolithic machine.
We need a team.
To solve the hardest problems, we need an MRI, an ultrasound, a CT scan, and a human specialist all looking at the exact same data, sharing their unique perspectives in real time. Thank you so much for joining us on this exploration. Take a moment today to reflect on how you structure your own human teams, and ask yourself whether you are building a fragile monolith or architecting a truly diverse, synergistic blackboard. Until next time, keep diving deep.